Hi, it's me again. I'm almost done with this. We have two very, very short topics to talk about to make sure that we have covered everything before you take the Regents. And I wanted to get this done a little bit sooner. Didn't work out. That's okay. These lessons will not take very long. First one, and it's kind of like an odds and ends. It's stuff that I need to cover to make sure that you have been exposed to it in the off chance that you get something, a question like this on the actual Regents. We're going to talk a little bit about the nucleus, just some, like I said, a collection of things that we need to talk about that all have to do with the nucleus, okay? We know that that's in the center of the atom. We know that the nucleus is composed mainly of protons and neutrons. Those are the particles that are in the nucleus. Particles outside the nucleus are things like electrons, okay? The only exception to the rule that the nucleus is composed of protons and electrons, protons and neutrons, is one particular form of hydrogen. Okay, the simplest possible form of hydrogen. That has a nucleus consisting of just one proton. And scientists have come up with a word that means anything that's found in the nucleus. Okay, if we want to talk just about anything that's in the nucleus, not necessarily protons, not necessarily neutrons, but anything in the nucleus, we call that a nucleon. Nucleon. Okay? That refers to both protons and neutrons, things that are found in the nucleus. If we take a look at this picture right here, we see a very typical drawing of an atom with our nucleus here, our electrons. This is wildly inaccurate just in terms of scale and what the orbits actually look like, but it's good enough for our mental picture of what a nucleus looks like. How many nucleons are shown in this picture? We just got to count the things that are in the center. 1, 2, 3, 4, 5, 6, 7. There are 7 nucleons here. If we want to determine what element this is, we need to count just the protons. There are 1, 2, 3 protons. So, this element is lithium. The number of protons determines what element we are dealing with. Okay? Now, this is something that always bothered me a little bit. As you're looking at a nucleus, and you're thinking about what you learned in a couple months ago when we were talking about electrostatics and electrostatic force, a very natural question would be, why are these protons sticking together? Protons are all positively charged. If you put two positively charged things next to each other, they should repel each other. Okay? And you might say, well, there's some neutrons in the way. The neutrons shouldn't cancel out that force because they're neutral. The protons aren't going to be attracted to that. They're not going to have any interaction with the neutron. Why don't the protons just push each other apart? Why don't they blow the whole nucleus up? Okay? So why don't the protons all repel each other away? Why don't they do that? Okay, it's a good question. A possible answer might be, well, the electrostatic force, yes, it's true that repels objects, or that can repel. Two positive charges will repel each other, but are there any forces that cause attraction? We know it can't be the electrostatic force, but I'm thinking of a different force that causes attraction. That could be, for instance, what about the gravitational force? Maybe the gravitational force is causing some attraction here. Okay, maybe that attraction is enough so that the repulsion of the electrostatic force is kind of canceled out. Let's see if that's the case. So over here, I'm going to determine the electrostatic force. You can look in your reference tables for this equation. The magnitude of the electrostatic force is Kq1, Q2 over R squared. By the way, as a note, protons in the nucleus are approximately 1 times 10 to the negative 15th meters apart. That is a tiny distance. The width of an atom is about 1 times 10 to the 9th meters. That's a billionth of a meter. This is a million times smaller than that, okay? A nucleus is approximately a million times smaller than the actual width of the atom. You can't imagine something that small. It's pretty much impossible. Anyways, that's going to be our distance between our charges. For the electrostatic force, we would then start the calculation. K is the electrostatic constant. 8.99 times 10 to the 9th newtons times meters squared over coulombs squared. That number is located in the reference tables. Now we have to deal with the charge. We have two protons. Protons are elementary charges, therefore they each have a charge of 1.6 times 10 to the negative 19th coulombs. There we go. And the distance between them is 1 times 10 to the negative 15th meters. Now, if you want, you can pause this and you can do the calculation yourself, but the answer for the force ends up being 230 newtons, and this is repulsive. I need you to appreciate that number. You have two tiny little protons that are next to each other, and they are pushing on each other with a force of 230 newtons. If 230 newtons is probably somewhere between a half, a third, maybe a quarter of your weight, and it takes all of your mass in order to cause that force. Two tiny little protons in the nucleus are repelling each other with that force. That's almost unbelievable. That is a huge force for some tiny, tiny little objects. Maybe the gravitational force is big enough to hold this together. The gravitational force is given by G, M1, big G, M1, M2, over R squared. R is going to be the same thing. We go to our reference tables. We look up big G. It is 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. The mass of a proton is also on the front of the reference tables. 1.67 times 10 to the negative 27 kilograms. All protons have the same mass. And they are this far apart. 1 times 10 to the negative 15 meters. Now again, I would pause if you want to do the calculation yourself. But you should just be able to look at this and tell this force is going to be smaller. Okay, look at the exponents here. That's not as big as 10 to the 19th. That's not as big as 10 to the 19th. This 10 to the negative 11th is way not as big as 10 to the 9th. Same number here. It turns out the force of gravity between two protons, 1.86 times 10 to the negative 34th newtons. And that's an attractive force, okay? That's the force of gravity that exists between those protons. That's not holding anything together. You've got a force this big and you're going to try and counter it with this? Not happening. There is no way gravity can hold this together. Gravity cannot hold this together. So the question is, well, what can? Okay. Turns out there's a force that we have not talked about yet because we haven't gotten down to the nucleus yet. There's a force stronger than the electromagnetic force, or the electrostatic force, whatever you want to call it, that holds these protons and neutrons together in the nucleus. It has a very creative name. It is known as the strong nuclear force. It's a strong force, and it's in the nucleus. Therefore, we're going to call it the strong nuclear force. The job of the strong nuclear force is to hold all those protons and neutrons together. Now, people paint all sorts of pictures about what the strong force is like. A couple of my favorite analogies are the strong force is like one of those old like carnival strongmen. You know, they got like the leotard on, they got the huge arms and a huge upper body and tiny little legs. One of the stereotypical images of the strong force is imagine one of those guys in the nucleus. He's super, super strong, but he's got tiny little arms. You can also think of like a T-Rex. T-Rex is big, bad, scary. The T-Rex can't reach out. You know, they're really bad if they're right next to you, but they can't reach out that far and get you. Okay, they got the tiny little arms like this. The weird thing about the strong force, the reason those images work for the strong force, is because the range of the strong force is very, very short. The strong force only works inside the nucleus. That's how tiny the range is, okay? Its strength is basically zero outside of the nucleus. So strong force only works inside the nucleus. That's why we say it has tiny little arms. It's like a T-Rex, okay? It can't reach out and grab things. Once it gets them, it holds them very tight, in close. But the strong force has no effect outside the nucleus. That's why we don't talk about it, okay, when you're learning about forces, all right? Switching gears a little bit. So that is how the nucleus gets held together. the nucleus and the electrons around it, people get confused about what is responsible for what. Okay? All of last year, you spent talking about chemical reactions. You started talking about nuclear reactions at the very end. We're not going to talk about chemical reactions here. The reason that chemical reactions happen is because of the movement of electrons, whether electrons are getting transferred or shared or lost or gained. Any chemical reaction is because the electrons are being swapped around by two different atoms, or two or more different atoms. Okay? That's how chemical reactions happen. On the other hand, nuclear reactions, things like radioactive decay, nuclear fusion, nuclear fission, those happen due to changes with the nucleons, the protons and the neutrons. Chemical reactions and nuclear reactions are not the same thing. They're very, very different. Chemical reactions happen with electrons. Nuclear reactions happen with nucleons inside the nucleus. What a chemical reaction does is it changes what types of molecules are formed. Okay? But chemical reactions do not change the types of atoms that are present. On the other hand, if you have a nuclear reaction going on, that can actually change the elements that are involved in that reaction. You can start with one element and you can have another at the end by adding or subtracting nucleons. The picture down below is a very brief description of that. You can see it, the picture on the left. I'll scroll down. The picture on the left is a picture of some elemental hydrogen and some elemental oxygen. Okay, those are how hydrogen and oxygen appear in the environment. H2 and O2 and another H2. They react to form this common molecule, H2O, water. Okay, so we have the same number, if you notice, 4 total hydrogen atoms, 2 oxygen atoms. Over here, 4 hydrogen, 2 oxygen. This is a chemical reaction. The types of atoms didn't change, just the molecules did. On the other hand, I have this picture right here. You have deuterium. Deuterium has 1 proton, so it's a form of hydrogen. Tritium is another form of hydrogen. It has 1 proton as well. The difference is in the number of neutrons. Deuterium has 1, tritium has 2. Okay, they're both different types of hydrogen. So we've got hydrogen here. We collide the hydrogen together, and what comes out is a neutron, that's not an element, some energy, and helium. We literally changed the element that was present. This is a nuclear reaction. Okay, that is a nuclear reaction. The first one is a chemical reaction. I'm going to stop that now before we go on to the next page.